Okay, so today really is up to you. So if you can think of your questions, like sit there, meditate, try to figure out what were the questions you left at your apartment. That would be good, because I really I'm done delivering material. I want you guys to try to figure out what it is that you're, that you need help on. Okay. While you're doing that, I thought I'd play around with this. This is the energy level diagram that we had. Let's see. Let me go over here and shrink that ribbon down. Yeah, okay. So I thought it would be fun to play around with the temperature dependence of our equilibrium system. So here we see at room temperature, why won't it let me select it? That's weird. It's selecting like above. There we go. I got it. That's strange. Okay. So 298, right? Room temperature. So our equilibrium constant that we calculated was 1.4. So it was forward direction, was spontaneous, and so on. But notice how it's entropy driving the reaction. It's endothermic, right? So here is the endotherm right there, delta H. So it's positive. So that means temperature is going to affect the equilibrium. So how could we get it to sort of shift back to the left? So whatever entropy effect is, temperature makes it bigger in terms of your Gibbs energy, right? So it's H minus T delta S. So if we want to make it positive, in other words, less negative, we could lower the temperature. So let's try that. That's so weird, that offset. Okay, so let's go, I don't know, give me a temperature. 600. Okay, let's go up. Let's see what we get. Wow, negative 218 is our delta G. So we got more spontaneous, and our equilibrium constant got bigger, 1.6. And so again, more temperature drives up that entropic effect, which drives it forward because there's more entropy going forward. So then let's go lower. So we were at 298. So our Gibbs energy is negative 75, and our equilibrium constant is only 1.4. So I'm just trying to give you a feel for how reactions work. So it's endothermic reaction, but it is spontaneous at this temperature. So let's cool it down. How cold do we go? Let's do 100. Then we'll do 37. Yeah, 100. So it was 1.4, and now it's 1.06. 1.06. And our delta G is only negative 4. Right, so we're cooling it down so that entropy is not as much of a factor. But now the delta H is kind of taking over. Okay, 36. Really cold. So now everything's in the ground state. Look at our population probabilities in our table. Ground state, and the ground states are at the same level. And so we throw our molecules at this, half of them are products, half of them are reactants. We're at equilibrium. Delta G is 0, equilibrium constant is 1. So that's great. So that's a fun type of reaction when you have endothermic and it's got entropy on the product side. Then temperature is what drives it forward and backwards. Now we don't really go backwards because we have this ground state here. This one right there. Okay, what if we deleted that one? So I'm going to delete that one. I'm going to make the degeneracy 0. That's an easy way to sort of just take that one out. Oh goodness, undo. Excel is really behaving weird. Okay, so I'm going to go down right here and just make that 0. Whoa! You see what's going on?
No, I think it's doing the right styles of the enter.
Uh-huh. You think it is?
I think it is.
Okay, so let me do 0. Enter. There. Yeah. Wow. Golly, that's so weird. I don't know what's going on, but yeah. All right, so that takes that ground state out. it's no longer a part of the calculation, because you remember it's the Boltzmann factor times that degeneracy, and I just said there's no level there, so I made a degeneracy of 0. I'm not going to do that to you in the test, but we're just having fun. So our delta H now is very endothermic, right? We see that it's 200 now because the products have no lowest, equal ground state. Their first one is up at 200. And so look at our K. It's 0.001 because, again, the lowest energy levels on the reactant side. To go to the products, yeah, we have more entropy, but it's up high and it's really endothermic. So it's not very spontaneous, but we're at 36 Kelvin. So let's go to 100. 100? Okay, 100. Okay, so our Gibbs energy has dropped. It was, what was it before? It was 182. Now it's 150. Okay, so it's getting a little more spontaneous. Our equilibrium constant is 0.15. It was 0.001. Okay, let's go to 298, so room temperature. Our Gibbs energy is still positive, so it's not spontaneous as written. It's 50, but we have 0.78, so it's still reactants favored. What was yours, 600? 600. Okay, now we got a spontaneous reaction. So negative Gibbs energy, negative 73, and a 1.12 or 1.19 equilibrium constant. Isn't that cool? We can drive this reaction forward even though the energy level, let's see, I want to scroll up. Okay, there we are. See, this is our energy level diagram. So we don't have that energy level at 0, but we can drive it forward with temperature. So we give the energy, enough energy to the molecules. There's more chairs on the product side, so they're going to just go that way because of entropy. Okay, well, does that spark any questions or anything like that? Again, I don't want to take up the whole time, but I thought this would be fun to play around with.
Will the reactants always be like single digit?
No. So it could be anything like that. You could have this whole thing reversed, with degeneracy on the reactant side and very, simple deal on the product side. Yeah. So you just got to look at the energy level diagram and make sure your G's match that, right? And I did it like ground state, middle, excited state. I think on the exam it's reversed. Like the ground state is on top row of the table, and then the excited state is the second row of the table. So pay attention to the table. It doesn't have to be like lower energy to higher energy. Just the sort of question generator I have has it reversed on that. So that would be one area where you might know what you're doing, but just screw it up because the table's, in opposite order. So pay attention to those. What will happen is the way I've made the problem is I've taken a problem kind of like this. The products, the reactants are all done, but like the products, like I'll take this and let's see. I've kept everything the same, but I've just made this text white so you can't see it. Right? So the problem is right, but you have to fill in some of those blanks. And so that's where 10 points is showing your work on filling in the missing blanks. And then there's a lot of multiple choice questions about those. And some of the multiple choice questions have numbers in there. So you can get like 5 points credit for each one of the ones I asked for, and then another 10 points just for showing your work on all of those. So this problem is probably a third of the test. Yeah, maybe even half. Okay, so if you feel comfortable with this, that's good. The other half is, questions about, is it endothermic, exothermic, that kind of thing. And endergonic, what is endergonic? What are you going to look for that? Gibbs energy. And endergonic would be what kind of Gibbs energy? You're outvoted. It's positive. Yeah, positive, endergonic. So it takes in energy, Yeah, negative would be exergonic. Yes.
So it's going to be a mix. So we're going to do like the math of it, like we did Wednesday, or is it going to be not conceptual?
It's mostly math. Yeah, it's
Okay.
mostly doing the math of all of it.
Okay.
Yeah, yeah. There's one where, remember, I really beat the drum on being able to work your way out of an equation. Like if this goes to 0, what happens to this piece? If that goes to infinity, what happens to this piece? You know, work your way out of the equation as to how it depends on temperature. There's one of those. That's 10 points. Yeah.
Is it going to be the equation you covered in class, or do you need to know them for all of them?
You should have all of the partition function equations on your note card. And all of these equations, the USHAG equations. So those are the main ones, and then be comfortable using Boltzmann's constant in different units, like whether it's joules per mole Kelvin or whether it's wave numbers per Kelvin. Yeah. I don't remember this if you do specifically for that one, but you need to be comfortable with that anyway, like throughout the whole course. And so it's, again, just use your units as a guide. And it's easy to know, like with Boltzmann's constant. Let's just do one of those. Let me pull up a PowerPoint. Sorry it's taking so long. It's just computer's acting slow. It's really being weird with that Excel thing. That's kind of strange. Oh, that's not blank. There we go. Okay, good. That works. Okay, so, you know, Boltzmann's constant, right? It's equal to 1.38 times 10 to the minus 23 joules per Kelvin. And let's trying to think of a scenario where you would need to use that. Entropy is equal to the average internal energy over temperature. Is it plus? I can't remember. Look at the equation for me. Plus or minus. This is why you need a note card, right? So it's plus. Okay. Plus, you know, it's R then Q. And R is joules per mole Kelvin. And I don't know if y'all saw me do this before, but you know, if I take this Boltzmann's constant and multiply by Avogadro's number, that's 1.38 times 10 to the negative 23. Oh goodness, what a 2 that is. Okay. You know, if I'm trying to get to joules per mole Kelvin, I should just be able to multiply this by Avogadro's number, which is 6.022 times 10 to the 23rd per mole. We never say the thing on top. You know, it's particles per mole, right? Or things per mole, just like a dozen. You know, a dozen is 12 objects. You know, so it's 12 per dozen. So a mole is like a dozen. So if we multiply these things, what we get is essentially 1.38 times 6.022. So it's a little bit bigger than 6. It's in fact 8.314 joules per mole Kelvin. So that's where that ideal gas constant came from. It's actually Boltzmann's constant times Avogadro's number, which is very cool. So, but if we had the internal energy and wave numbers, then we wouldn't use this. We would use, and you know, this R is K times NA. But if we're looking for something in wave numbers, we would do K over HC. So you see, all of those are just different versions of K in different units. So that's why I say you have to be comfortable in swapping out the units by dividing by Planck's constant or the speed of light or something like that. Now, typically we write, like if you have the speed of light memorized, what would you say the speed of light is? Yeah. 3 times 10 to the what?
8.
Yeah, very good. 8. But do you know what the units are on that? Meters per second, right? But if you use that, then you're going to end up with inverse meters, not inverse centimeters. Okay, so that's gonna mess things up. So if you swap that out to 10, then you have centimeters per second.
Oh, okay.
Yeah, so you can totally do that. It's 3 times 10 to the 10th centimeters per second, and then you'll get the wave numbers that you need. So that's a simple place where people get off by 2 orders of magnitude, and they're like, oh no, you know, I don't see the answer in the multiple choice. I'm 100 times off.
So let's say I forget that that's a problem, and I do today. I'm gonna try not to, but let's say I do. Will the answer still be right, just magnitudes off, or will the answer?
It should still be right because you multiplied or divided by 3 in this case, right?
Okay.
Yeah. So it should still be right, but that would be if you're just using it to calculate, you know, K.
That's if I just.
But then if you put it into that equation up there, then who knows, because it's going to screw with the natural log of Q, and then the U and the T won't be off by that amount, so you will have totally different numbers.
So it's only a small issue for starter. If I keep going, it's going to be a problem.
Yeah, right.
Okay.
But that's why that's why, again, this is such a common thing right here, that it's good to just have these constants, you know, on your card. And in fact, they're actually on the periodic table that I pass out. Oh. So this one is on the periodic table, 0.695 wave numbers per Kelvin, because it's so common. And R is, you know, 8.314. But you just have to know, oh, if I've got my internal energy in wave numbers, I better not use an R in joules per mole Kelvin, because those units don't work, right? So that's the thing that I really am interested in, to make sure you don't make that kind of mistake, because that is really a bad mistake. When you've got wave numbers per Kelvin and you're adding joules per mole per Kelvin, you know, those you just can't add those. You got to get them into the same unit to do the addition.
Do you have the equations posted already, or?
No, you have to put these in your note card. So like these equations here, the USAG equations here.
Oh no, not that one. The ones you're giving us that constant, just so I don't like.
Yeah, you could save some real estate on your note card.
Yeah, because that's something I want to put on there.
Yeah.
I don't have. Do you have periodic table?
Yeah, I'll pull it up.
Yeah,
I'll pull it up.
Just so I know what I can.
Yeah, you know what you're getting. Yeah.
Yeah.
I typically have it on Blackboard, but I don't think for this course it's on Blackboard. And if it is, I don't know that it's readily, or if I could point you to it. So let me go find it. It's under teaching. Yeah. That's right. This is valuable real estate on that. Here it is. Periodic table with constants. Okay. And let me go over here and grab it. Yeah, display captures on. So, yeah, there it is. Okay, so then let me bring this window thing up. So let me zoom in on that. It won't zoom. Oh, yeah, there it goes. Okay. Nope, don't do that. There they are. So you've got Planck's constant in joules per Kelvin. You've got Planck's constant. It really should say K over HC to be technically correct. 0.695 wave numbers per Kelvin. Avogadro's number. You have the gas constant for using the ideal gas law, liters, atmospheres per mole Kelvin. And then you've got the gas constant in joules per mole Kelvin. Faraday's constant, which we won't use until later in the semester. I've got some conversions over here. When you're doing Gaussian calculations, here's Hartree to kilojoules per mole. So that's kind of nice. 1 calorie with a lower c is 4.184 joules. The capital C calorie is a kilocalorie. So I don't know if you all knew that, but that's on here. Electron volts in terms of kilojoules per mole. So that's handy. Conversion of pounds per square inch to atmospheres, grams to pounds, and centimeters to inches. So, yes.
So going back to the whole
Mm-hmm.
is there a certain number of decimal points I'm supposed to be going to?
That's a good question.
I know it was in the homework, and I got it slightly off, and I marked it wrong, and I don't know what I was supposed to be.
Yeah, so my effort, at least especially on the multiple choice, we have 5 numbers, and you're like, okay, it doesn't hit any one of those. You should pick the one that it's closest to. So like if it's 50 is, answer B, and you do this calculation and you get, 47. I mean, it shouldn't be that far off, but it might be, right? And so you're like, well, that's 50, because I typically don't do like A is, 40. Let's see, 44. Okay, that's a bad situation, man. You're a 3 between. Right. Yeah, that's right. But did you round up or down, right? I mean, if you go, 47 is halfway between 44 and 50, so that's a problem. And so I try to spread my answers apart enough to where you're like, okay, I've got a rounding error. It's closest to 50, so I'm going to go with that. Yeah. So.
I multiplied 1.38 plus 6.023 on my homework, and I got 8.312, and it marked out wrong.
Really? Because the tolerance is, which homework was that? Number 2. Okay, let me see. I brought them all to class. And which problem? Question 4. Okay. 8.3145. Okay.
I don't know what I'm supposed to be multiplying when I...
Well, I mean, I did plus or minus 1 in the third decimal place. So we missed. So that for that one, I guess I had a higher precision than I typically do. Number 4. I guess for the constants, I had a really tight tolerance. But like on number 1, when it says, what's the probability of being in the ground state? The answer was 35, and I put plus or minus 1. So like that was a huge tolerance because you might get 36, that'd be okay. If you got 34, that was okay as well. But for the constants, I had a tight tolerance. So maybe I should put on there you know, tight tolerances use 5 significant figures or something. Yeah. So let me write myself a note.
Number 2, number 4 was asking about probability.
Which one? On the homework 2?
Oh, because number 4 was probability.
Oh, on the homework
On
it's
the
switch.
handout and on Blackboard, the questions are in a different order.
Yeah, I'm using the printoff for Blackboard.
Oh, I'm using
Okay.
the handout. I was like,
Okay.
Two on the handout.
Got it. I was
Okay.
like,
I'm
guys,
sorry for that confusion,
I don't
too.
think we're talking about the same thing.
Yeah.
Oh, this is not.
Yeah.
So should I have pulled up more decimal places?
Yeah, so if you would take Boltzmann's constant instead of 1.38, but to actually get a couple more decimal places there, and Avogadro's number, I mean, we typically have that memorized to 6.022. But you know, if you wanted a 5th decimal place, you need to look it up. And there are, in one of the lectures, I have like 6 decimal places listed for those constants. But it's all at NIST. I'll leave a link in the notes for the NIST website where those constants are. It's good to be familiar with that webpage, because if you are going to be doing work that you know, if you're building something that's going to go in the air with people in it, you want to make sure that you use all the decimal places. You don't want to round up. Good questions. Keep them coming. You want to do a Kahoot?
Sure.
There's a USHAG Kahoot, one on all the USHAG equations that we haven't done yet. Oh, you want to do more homework? Okay, let's stick to that, because that'll help you directly. I mean,
Okay.
Okay.
I have a question.
Yes.
It was homework 3. It's on the actual handout. But I was not getting, like 11 through 16.
Yeah.
I just was not getting them right. And then once I took it twice,
Yeah.
I got the answers.
Okay.
I was not getting them. I tried them, like,
Let
I
me
don't
see.
know if I'm using the wrong.
You're talking about homework 3?
Yeah.
Let me pull up the key, and I'll bring it over to the right side.
Because
Okay, there it is. Let me zoom in.
it was like,
Come on, where are you?
just like the NRT stuff. And NRT and things like that.
Yeah.
But I don't know. When I have choices, I do well. When I have to find my own answer,
That's right, and that's why I've done that a lot more on Blackboard. It's like making you come up with your own answer and put it in, right?
Yeah, I was not.
Yeah.
I was getting close, but I wasn't getting the right answer, so I don't know.
Okay. So, are y'all pretty good on these? The smallest energy level spacing, the largest energy level spacing? Do y'all understand the different kinds of energy level spacings we have?
Yeah.
Okay, so the best way I can think of this is to think of the stairwell. The stairs are our idea of quantized states. You can be on stair 0, 1, 2. Those are quantum states. The distance from stair 1 to 2 is what changes. So think about translational energy levels, and then think of like a ream of copy paper, right? The individual sheets of paper are the translational energy spacings. So if you set those by the stairs out there, look at the spacing of the translational levels. It's as thin as a piece of paper, okay? The whole ream of paper, like stacks of those papers, that's like rotational levels. Okay, and then the stairs themselves will be vibrational. So you see the vibrational levels are bigger spaced than the rotation, and rotation is bigger than the translation. And remember, it's just statistics. So if I throw molecules in at room temperature, those translational levels are really populated. There's thousands upon thousands of them that have molecules in them. And there's hundreds of rotational levels that have molecules in them. And then for vibration, there may be 1 or 2 or 3, that have molecules in them. And then electronic, they're all in the ground state. Electronic would be the floors. So floor 2, 3, and 4 would be the electronic levels. And at room temperature, they're just not going to have molecules excited up on the 2nd or 3rd floor. Does that mentally help you? Yeah. Okay, good. I thought about marching us out in the hall and setting some paper by the stairs and all of that, which would really be cool, but anyway, I'll just describe it to you.
You said vibration is bigger than rotation.
Yes.
Bigger than
Yes. Yes. Yeah, and electronic is the highest.
as far as like step size?
Step size, and step size in this case is energy, right? So if it takes more energy to step up on a stair versus a piece of paper, you know, that's the difference between going up in vibration versus going up in translation. So the translational energy levels are like thin sheets of paper.
So sorry, did you say it's translation and then vibration, or translation and then rotation?
Then rotation, then vibration. Yeah.
I have a question about number 4, where
Okay.
it was saying for a small molecule, which partition function contributes most to or lower entropy.
Yeah.
And it was translation. I didn't understand. Is it kind of like the energy spacing, like in terms of translation, rotation, partition?
Yeah. So the entropy, no, the entropy is related to that partition function, and if it's bigger, then the entropy is bigger. Okay, and so then the partition function is a count of the energy levels that are populated. So translation is they're so close together, there's thousands upon thousands that are populated. So the entropy is really driven by translational motion. So that's why when you make more gas molecules, the entropy goes up. So in a reaction, if you see gas molecules on the right and no gas molecules on the left, entropy really goes up in that reaction. So that's driving it forward for terms of spontaneity.
So for number 12, what am I supposed to
12,
do
here we go. Okay.
from the question to know that only one state is active? Like, that my A equals 1?
Yeah, okay. So you know, let's see, I'm going to I'll snip this. Okay. Some advanced tools here. Maybe I'm asking my computer to do too much. Let's see. There we go. Don't worry. So this is number 12 you want? I'll do both of these. How about that? Okay. And then I'll come over here. Yeah. And then I'll go back to that one. There. Isn't that nice? Now I can draw on the problem. That's what I was aiming for, so I can use my pen. I can't use my pen on a PDF. Okay, so I'm looking at this problem, and I've got a single normal mode of vibration. That's what tells you A is 1. Okay, so for this molecule, I have 3n minus 6 modes of vibration. And in our CV, our CV equation, CV is equal to, you know, for translation, it's 3/2 R, and for rotation, it's a nonlinear molecule, so it'll be 3/2 R for nonlinear. Does that help everybody? Plus, and it was A times R for vibration. And A can go from 0 to 3n minus 6, right? So that's the full range of A, and we're figuring out, your question is a good one. How do I know from the text in this question why A is 1? And it's just because we're talking about a specific normal mode of vibration. We're only talking about 1. And so it's saying if this 1 is activated, what would be the contribution. Does that make sense? Yeah, because it's A could be 0, which it typically is at room temperature. Or if it's like the maximum, it would be 3n minus 6. And since A is 1, then it's R is 8.3. So this is the answer that I was looking for with its tolerances, 8.3 plus or minus 0.1. So like you could say 8.3145, and you would have gotten it right because it was plus or minus 1 in the first decimal place. So that's how you know A is 1. And we're only looking for the vibrational contribution. What would be the dihedral normal mode of vibration? What would it contribute to the constant B molar heat capacity? Okay, the next one is what's the rotational contribution. So we calculated that up here. That's this 3/2 R. So yeah, 3 halves times 8.3145 joules per mole Kelvin. So you can say 3 times 8 is 24. 24 divided by 2 is 12. Okay, it's a little higher than 8, so 12.5 makes sense. But you have to supply your own answer, which is what you were saying you didn't like.
Yeah, I just like,
yeah.
was not, like, I think for 12, about 11.4, I don't know where that came from.
Uh-huh, yeah.
I don't know how that happened.
Yeah.
But it did. And I wasn't, yeah, I don't know.
Yeah.
Because I knew that it was this, like, area. But
right.
I was not. Yeah.
So what if I ask you a trick question and say, what's the vibrational component?
I probably wouldn't realize you were tricking me.
Yeah, I know. That's why I'm doing it now. Okay, I'm trying to trick you. What is the vibrational contribution to CV for helium? I can say max, right? I'll say max, right? Because then you're thinking 3n minus 6, right? Yeah, yeah. So do you see why it's a trick question? Because helium's just a single atom. And I'm asking about vibrations. You can't have any vibrations if you just have a single atom. Because it has to be 2 atoms vibrating against each other. Yeah. And so that's what makes it a trick question. It's a single atom, so it can't have any vibrations. What about rotational components? Still 0 because an atom can't rotate. You can't tell if it rotates. The mass is in the coordinate system, the mass is at 0, 0, 0. There's nothing off the axis to create a moment of inertia in which you would tell if it was rotating or not. So you have to have at least a diatomic to have a rotation or a vibration. But if you have just an atom, only thing you have is translation. Not a fan, huh? But see how that's an understanding question, not just a procedural calculation question. So that's where we want to go for some of these. Problem like that looks really easy, but it's actually more difficult than 12 or 13. Because you have to understand the concept, not just say, oh yeah, I've got this equation on my note card, I'm going to start plugging in numbers. That requires less thinking than this kind of problem. So, what if I asked you which is larger, the heat capacity, CV, for helium, for nitrogen, N2, or water? So helium, nitrogen, or water. So let's do that one. Well, I'll leave it here and I'll just erase this stuff down here. So there you don't even have to calculate anything. So which CV is largest? And this is an easy one to answer, right? Helium, I mean, there's three choices. Into H2O. So look up here at this equation, the heat capacity. All three have translation. And is the mass in that equation? No. So you don't have, doesn't matter that nitrogen is heavier than water or heavier than helium. So mass does not matter. The only thing that matters for translation is this is equipartition. You know, they're a certain temperature, they have this much heat capacity, okay, for the translation. What about rotation? We know helium doesn't have any rotation, so it's missing that piece. So it's not the largest one. So we can eliminate helium. It's not the largest. And this is 3 halves. It's greater than 1. It's gonna add something to this. But we have nonlinear versus linear. So which is larger? The linear is 2 halves R. It's smaller. So this is the smallest. This is CV is equal to 3 halves. Come on. I got to draw really big 2 because of this little context menu down here. 3 halves R. This is 3 halves R plus 2 halves R. We'll just ignore the vibrations for now because, again, those are not relevant at room temperature. So we're going to leave that at 5 halves R, and then water is 3 halves for translation and 3 halves for rotation. If, let's say you weren't paying attention and you thought, well, I didn't clue in at room temperature, vibrations aren't active. And so let's say you included the vibrations. How much would we have for the vibration of nitrogen? Let's pretend that one is active. Yes, so we'd have just one more R for that because we just have one vibration. But over here, how many would there be for water? So we have 3n minus 6. So there's 3 atoms. So 9 minus 6 is 3. So we'd have 3R for that. So even then, even in that situation, water would be the higher one. Okay. So that's a good question. You get it? For water, because there's 3 vibrations. And I know that because of this 3n minus 6. This is calculating the max number of vibrations. And so that's what this A goes from 0 to 3n minus 6 in terms of A being active vibrations. But the maximum is 3n minus 6 for a nonlinear molecule.
Since you're asking for the largest molecule.
Yeah, the max, yeah. But I would say even if you were to just look at room temperature, that water would be the highest as well because it's nonlinear versus linear. Yeah. Yeah.
For A, it can range between 0 to 3.
Yeah, because A is it active or not at whatever temperature you are. So A is temperature dependent. 3n minus 6 or 3n minus 5, those are the maximum values. Let's do this one. Where did I get the 1 vibration here? That was from 3n minus 5. 3n minus 5 max vibrations. And it's minus 5 because it's linear. So I have 2 atoms. So 3 times 2 is 6. minus 5 equals 1. So that's why we only have one vibration for nitrogen. Plus that one's pretty obvious. You got two atoms, only thing it can do is vibrate. But for water, I can do my little, symmetric stretch, right? My head is the oxygen, my hands are the asymmetric stretch, and the bending. So those are your three vibrations for water. You can think of it as the three variables too to describe that structure. You have two bond lengths and an angle. That's all you've got. Every one of those can change. So there's your three vibrations. It just so happens that the bond lengths couple with each other because they have the same spring constant. So they couple together or opposite. But it's still, you have two bond lengths, you're going to have two vibrations. You have an angle, you have a bending motion. Yeah. But that's last semester. Oh, it's 8:52. Wow. But I think we covered the main stuff that I put on the test. So I think nothing's left out from my memory. I made it yesterday, so it's still kind of fresh in my mind. So I won't be here. Kaylee will be proctoring the exam because I got to tell the vice president who to hire for the dean. So,